we do photography at the speed of light. And of course, the question now is how do we do that, and that's what we will explain in the presentation. But first of all, let's think about something basic. If we think about the word photography, photo is the Greek for light. And if you can see me right now, it's because there's light coming from light sources on the ceiling. Light travels to my body, then it's scattered from my body to your eyes, and then your eyes send the signal to your brain.
But when we say that light is coming from up there and then it scatters towards your eye, that implies that light is moving. And you could ask whether that is true. Is light moving, or is it instantaneous in the sense that you switch it on and the whole room is flooded with light, right? And if it is moving at a finite speed, what is that speed? Now, one of the first who tried to see whether it is moving and how fast it is moving was Isaac Beckmann in 1629. And the way that he did it was that he was standing on one mountain, and then a friend of his was standing on another mountain, and he was holding a mirror. And we brought the mirror here, and I brought my bike light, because we will try to do the very same thing. So what he did is he switched on a light source, and then he tried to see whether it takes some time for the light to get back to himself, right? And in this way he tried to measure the speed of light. So let's see whether we can do it. No, it doesn't work, of course. Oh, okay, the light is on, but to be honest, I couldn't tell. And that's the same answer to the question that he found in 1629. He simply couldn't tell, meaning that either the light travels really fast or it's instantaneous. So what do you have to do if you want to measure the speed of light? Well, one thing you could do is you could increase the distance between those two mountains such that it takes a longer time for the light to travel back and forth. But that also means that you need a more intense light source, right? And he already used some gunpowder that he exploded, so it was already the best light source that he had at that time, right? So what you could do at the time to look at the distance that is way longer than the distance between the two mountains here is you could look to the sky. And this is what Ole Römer did 30 or 40 years later. And more specifically, he was looking at the moon Io that would travel around the planet Jupiter. And it was known at that time, and he also could see it, that this happened every 42 hours. And he would always note down the times at which the moon Io would hide in the shadow of the planet. So if it happened on this day at this time, he could tell, well, the next time it should happen on the 21st, sometime, I don't know, 9:20 or so. So let's see whether it's true. Yes, so it works out. It's hiding every 42 hours. And it does so again now on the 23rd at sometime early in the morning. So he could say, well, if this happens every 42 hours, then I should also be able to tell when it will happen in 3 months from now, right? It should happen on a certain date at a certain time. So let's see what happened during that time. If you wait for such a long time, the Earth also travels around the Sun. And this means that now the distance between the moon Io and the Earth is much longer. And that means that if light moves at a finite speed, it will take a little bit longer. And indeed, that's what Ole Römer saw. He saw that now the moon Io would hide in the shadow 20 minutes later than he would have expected. And from this time he could say, yes, light travels at a finite speed, and he also got a value for the speed of light, which was already really close to the value that we have now, which is 299 million meters per second, so about 670 million miles per hour, which means that if those two mountains here were at the distance of 120 yards, it would have taken the light only 0.0000037 seconds, and that's why I couldn't tell, and that's why Isaac Beckmann couldn't tell. Because this is simply a time that is way too short for our vision to grasp that. And of course you could question that too, right? Is our vision really that slow? So we will try to prove you now that your vision is as slow as mine, which is way too slow to ever see such short timescales. So what you see here now on this tiny screen here is you see a square that's going on and off. So white, black, and it will blink faster and faster. I hope that you can all see it. Maybe you can hold it up a bit. To the point where it will be hard for you to tell whether it's on or off. So right now I can still tell whether it's white or black, but now it's already kind of getting fast, so it seems to my eye, it seems to flicker a little bit. Now it really does flicker, and now it seems to get more and more gray, up to the point where you just cannot tell whether it's white or black, right? And that happened at a period of 10 to 30 milliseconds, so at about 50 to 100 hertz. And this is the reason why your computer screens run at 100 hertz. And this is the reasons why movies are taken at 30 frames per second or maybe 60, because you simply couldn't see any faster than that. There's no use in making a movie at 1,000 frames per second because you couldn't see it, right? Which, of course, means that there are things now if we say that light is that fast, light is much faster, and that means there are many things happening in this world that are so fast that we cannot see it. So I just want to give a short introduction to the time scales that kind of govern our life. You all very, very, very well know that the time scale of our heartbeat, right? It beats about once every second. If you don't like physics, it might be much slower now. Mine might be a little bit faster now. 1 billion times longer than that, that's about 32 years. That's about my age. 1,000 times shorter than 32 years, that's about 12 days. 1,000 times shorter than that, that's about 16 minutes. Now you all know what 16 minutes are and what 12 days are. I'm just putting it up there so that you get a feel for what the fact of 1,000 means, right? Many more things can happen in 32 years than in 12 days, because now we will go the other ways. We will make our time scales 1,000 times shorter and 1,000 times shorter and so on. So 1,000 times shorter than our heartbeat, that's a millisecond. That's the time it takes a housefly to beat its wings. That's the time that your shutter takes to shut in your mobile phone camera. 1,000 times shorter than that, that's already a really short time. In this short time, a fastball, if you throw a really fast fastball, then it only moves by about the width of a human hair. So it looks like if it was standing still, but time still passes on, of course. And 1,000 times shorter than that, that's now a nanosecond. And on one of the last slides, we've seen that in 1 nanosecond, light moves about 1 foot. So light is that fast, and in that short time, it can move that far. And 1,000 times shorter than that, that's a picosecond. That's the time scale on which a chemical bond forms and breaks. So in nature, many things are going on this very short time scale. It all wiggles around. We will show you some movies now, or soon, that happen on this time scale, that happen on the picosecond and on the nanosecond time scale. So we will follow a pulse of light with frames spaced by about 50 picoseconds, and we will follow it over the course of about 10 nanoseconds.
So one of the first pictures taken at this very short shutter times, like between here and here, was actually taken already in 1976 in the Bell Labs. It shows a bottle filled with a scattering liquid and a laser pulse moving from right to the left. At that time, they had already shutter times down to 30 picoseconds. So in order to capture the speed of light, one needs 2 things. So you need a very short laser pulse, because if the laser pulse wouldn't have been long, then you would just have seen here a line. As well, you need a very short shutter time. So if you want to make a picture of a fast moving car, you have to somehow freeze it in time. Mechanical shutters of analog cameras are constructed by mechanical parts. Mechanical parts can never move fast enough in order to capture the speed of light. So how do we do in our case it? So we capture a photon which got scattered from an object collected by our camera lens. Then the photon gets converted into an electron, and now we use a fast switching electrical field, an electrical field, in order to gate the photon, the electron now, or to block it. It's the shutter here. That happens really fast. Afterwards, if the electron is gated, we amplify the electron to a lot of electrons, and now we convert the electrons back to photons, and in the end we collect it on our CCD chip. So here you have seen what happens at a single pixel but we want to make an image of it, so we need a lot of pixels. In our case, we have not 3, but like a 500 times 500 pixels. So now we have the camera, but how does actually look like the procedure? How do we capture or make a movie of the light moving? So for that, I would like to show you a short animation. In the background, you see our lab in Stanford, and a laser pulse, a short laser pulse, is released from a laser, focused through a lens, in order to get afterwards expanded over the whole room. So now we have our camera, and with the camera we can capture the light at a certain time. And a certain time means for light at a certain distance from the laser. So we capture the light at a certain distance from the laser, and for the next frame in the movie we wait a little bit longer, where the light has moved a little bit further. With that we can actually make a movie of photography of the light writing. Photo stands for light and graphy for writing.
So now finally we are going to show you some examples of the videos that we've done using this technology that Phillip just explained to you. This first example, I want to let you know that on the left side of the screen is what we call a traditional picture. So a picture of a scene if we could have done with a traditional camera. And then on the right side you are going to see the same scene, but this time we are capturing the image with this pulse of light that you will see moving across the scene. And what it's represented here, it's a cardboard scale that we created at the beginning, that we were trying to figure out how fast this pulse of light was, like how it could move through different objects. And it has, we put like black tape on it every 1 foot to see how light could move across it. And as you will see at the end of the film, when the pulse of light reaches the wall, the background, you see that it gets in the center first. And that's why what it was also seen in the animation that Phillip showed to us. The next, of course, we just didn't do scales. We also tried to capture the motion of light moving across daily life objects. And I'm going to show you another example, and I'm not going to tell you what it is until the next slide. And I want to let you guess what it is. So if you thought that it was a plant, you guessed it right. Again, I'm going to show you the traditional picture on the left side, and again the video on the right side, so that you can see that when the pulse of the first parts that get illuminated are the ones that are closer to the camera, because of course the pulse comes from the camera and then it moves towards the background. And we were very fascinated with this plant. Actually, it was a plant that we took it was in the corridor of here in Stanford, and we wanted to see what could happen, how light could move through other plants, because we really love the motion of light on the leaves. So this is another example of another plant. And again with the traditional picture next to it. What we really liked when we were talking about this is that first we are seeing the plant without the shadow, and then at the end we see the shadow without the plant. That was also very interesting for us to think about. And also very interesting for us was working here in a physics lab where Thomas works, because in Stanford, also 140 years ago, there was a photographer called Edward Muybridge that was developing also something similar to us, so very fast photographic techniques. I'm going to show you one of his most most pictures. He wanted to see with the camera something that people couldn't see with their eyes, yeah, very fast motions. And he did a lot of different studies with animals and people. And this picture made him really, really famous because he could confirm his theory that there's a moment in time in which a horse, while it's running, is not touching the ground with any of its legs. And thinking a lot about Muybridge and what we are doing also with our fast techniques, we wanted to pay an homage to him, and that's why we came up with the next video. And of course we couldn't bring a real horse to the lab, so we used this plastic mask. But yeah, I want you to notice that whereas Muybridge was using light to capture the motion of a horse, we are doing the reverse. We are using the horse to capture the motion of light. And of course, I mean, we live in 2016, and one of the trends in photography right now, it's called selfie. So of course we also did some selfies in the lab. The first one is Thomas. So as I said before, the parts that are closer to the camera are the ones that get illuminated first. So you see now, you saw first the legs, and now you will see the torso, and then the face, and then the background. And the second video, it's me. So again, the legs, the hand on the chair. You will notice that we are using goggles. That's not because we wanted to do a summer Californian portrait, but because the laser that we are using is very strong, so it could damage our eyes. And we were joking that if we couldn't make it to any museum, maybe we could make it to a laser safety guide in the section of please don't do these things. The third portrait is Phillip. And I want you to notice that when the light gets in the background, when the pulse of light reaches the background, there are small circles forming. I will try to point, yeah, like this. And that's because there are tiny bits of dust in some of the optics that we use. And I'm going to show it to you again, all of the three portraits together. And I have to say that the ears of Thomas get illuminated for a too long time. We don't really know why. You will see.
Well, yes. We have a little bit of time left, so I would like to talk a little bit more about physics. One thing to take home with for you is, of course, that light travels at a finite speed, so it takes some time for light to go from A to B. This means that, when you look at me now, the picture you see is an image from the past. Any image, anything you see is always an image from the past. Even when you look into the mirror, you see a younger version of yourself. That's one thing to take home with. The other thing is a small riddle. We have seen this video here many, many times, and you saw that the light is moving at a constant speed across this ruler, and then all of a sudden, when it hits the wall in the back, it seems to move much, much faster, right? So you could ask the question of whether there's anything here that's moving faster than the speed of light. And I'm sure that you can solve this riddle, and if not, you can send us an email. And if you want to see more of our movies, they are on seekphotography.com. And I would just like to thank Brennan Klopfer, who sits in the back here. I have the great pleasure to work with him in our lab. and he helped a lot with the code that we need to control our laser here. So he did great work, and I would also like to thank my boss, Mark, who did not fire me after we misused his lab for the movies that you've just seen. Thank you.